Okay, so hello everyone. Uh, Welcome to my seminar, and today we will be talking about modular spaces. Let me quickly close my browser so that I don't know if you can hear any noises, but just in case. All right, so today I wanted to introduce you to the idea of what a moduli space is. So this talk will be mostly informal. Moduli space, the theory of moduli spaces is a very rich topic, especially in algebraic geometry, but it is a rather technical one. So I have opted for just giving you the basic gist of what it is like. And for that, my goal is to give you one toy example, which will be the example of the projective line, or more generally projective space, and how it arises as a modular space, and then talk a bit about some modular spaces which have some very high importance in algebraic geometry, namely modular curves. But first things first, what is a modular space? So this all comes down to something called moduli problems. So the premise is that we have some objects which we want to classify. Say up to isomorphism. And we would also like, for various reasons, for example, putting perhaps just by this natural idea of putting some geometric structure on whatever we encounter, we would also want some geometric structure on classes of those objects. So I'm not going to be too formal on what I mean by geometric structure here. I am just, for the most part, I am just going to leave it up to intuition. And the basic example, as I have already mentioned, is going to be the problem of which will be solved by projective space. And if you have already, if you already know about something about it, then you might know that this space classifies lines in this case r squared, or more generally in the space r to the n. Okay. So the situation is this: we have some plane. This is just r squared, and we fix the origin, and we are interested in the lines going through the origin in this plane. So we have like pretend they are all going through the origin. We have this family of lines, and we would like to have some space which classifies those lines. And how could we construct such a space? Well, in this case, it is not terribly hard to do. One way we can do this is we can note that if we inside this plane consider the unit circle, then this space almost classifies the space of almost classifies the lines going through the origin, except every line, instead of having 1 point on the circle, it has 2 points. So what we have here is the kind of space of all lines is going to be this circle here, except we have to identify all the opposite points. So this will be some kind of quotient space. A bit easier to visualize is if instead of taking the whole circle, we just take a half circle. So we take some half circle like that. And then we see that all of those points are going to, all of those lines are going to have exactly one intersection point, except for this single line here, which has two intersection points. And this is, and to get rid of this ambiguity here, we again have to do some quotienting out here. We have to identify those 2 points. If we were to be in 3 dimensions, so say we are now in R3, this is a very bad cube, R3, then something similar we can do is instead of taking a circle, we can consider a sphere or a half sphere contained in this space around the origin. And then we again have to identify opposite points of this boundary of this hemisphere right here. So we can see that there is some, that it is still going to be some kind of a surface. But the boundary here is going to be a little complicated. So this is going to be, this is what is called, the resulting surface is something that's known as a projective plane. In this case, we get a projective line, but we see that with this identification, this is isomorphic or homeomorphic to the normal circle. Okay, so we have constructed some space, which is denoted RP n minus 1. Let me write it like this. And let me say that whose points classify lines in R to the n. Okay. But here's the question, and this is in this theory, this is kind of the most important question. Is this the right space to classify those objects? A space here, I mean just a topological space, but moduli problems, moduli spaces are kind of more general than that. You can consider those to be some kind of algebraic varieties or something like that. Here I am just dealing with topological spaces. Okay. Okay. So what do I mean with this being the right space? Well, it isn't exactly straightforward to answer, but one way to see that there is possibly some ambiguity here is that we can note that, for example, in this case of R squared, I could have also taken this semicircle to have only one endpoint and not have the other endpoint. And then I wouldn't even need to do any gluing of any sort. We would have just an open semicircle with one endpoint. And this would also be a space whose points classify all the lines in R squared. You can do something similar in R cubed or any other Euclidean space. But definitely, if we were to just throw away, if we were to throw away just one endpoint of the circle, then this doesn't exactly feel right because this space is somehow asymmetric. Because, for example, this point here somehow looks different than all the other points. Is the endpoint of this interval, and all of those are its interior points. Well, if we look at just lines in the plane, then it shouldn't be that any single line is somehow distinguished among all the possible lines. So it definitely feels like of all possible answers to this original questions, how to classify points, there are some wrong answers, but it doesn't, at this point, it's not exactly clear what it would mean to be a right answer to such a question, or if we somehow made sense of that, whether this would, such a space would exist. In the theory, the question is, do you mean this is not a homogeneous space? Yes, so this is what I was alluding to. So this point is somehow not the same as all the other points, but we would feel like the kind of classifying space should be a homogeneous space, because kind of the space of all lines is in some informal way homogeneous. In the theory of modular problems and modular spaces, this is actually resolved by a notion of not just considering single objects like those lines through the origin, but of families. So the key idea is families. So what does that mean? If we have some family, then it should be indexed by something. And since I'm working with topological spaces, I would take some topological space X, and I, instead of considering a single line through the origin, I say that a family of lines in a plane over X is a closed subspace of X cross R squared. So let me try to draw it. We'll have some space like this. This will be my X. And then over every point, I imagine that I have drawn a plane. Like this, roughly. And then so this is my whole space. So this is going to be X cross R squared. And I want a closed subspace such that over every point, maybe let me write this more formally, such that for every X in X, the intersection with X cross R squared is a line. So this means that our space looks like this, that for every such section of the plane, I am going to be choosing some I'll be choosing some line, and those lines can somehow vary as we traverse this whole family. So here we have this family of lines which somehow goes around and twists as we traverse the space X. This is a little bit of an ugly picture, but this is approximately what it is going to look like. It is going to be like a ribbon inside this space here. Okay, and those guys here can also be identified with line sub-bundles of a certain vector bundle, if you know what that means. If you don't, then don't worry about it. It's just to highlight that there is a language of bundles in which this is like a very natural construction. All right. And now it turns out that this space RP1, which I have defined above, is is in a sense the right choice of the space to consider here, because it turns out that such subspaces are in one-to-one correspondence with continuous maps from this space X, this is our base space X, to RP1. Because if we have any space, any subspace like this, then we can map each point X here. It is going to go to the point in RP1 corresponding to this line. In this picture, it will be this line here. And every other point can be mapped to RP1 this way. And it turns out that for any RP1, for any such family of subspaces, we have such a map which is continuous, and conversely, any continuous map is going to give rise to such a space. I get a question by identification with a graph, but I'm not sure what this means. I'm going to wait a second in case you would like to clarify what the question is. Perhaps what I have just explained answered this question. Fx to RP1, then we take x. Yes, so it approximately does work like that, except not precisely. So the question is whether if we have such, so if we have such map X F to RP1, so this is a bit of a tangent to answer the question, then we can consider the graph of F. It is going to be a subspace of X cross RP1. So given such a graph of a function, we could also use this graph to construct a subspace of, so this is going to be a subspace of X cross R squared, where we take that if we have a point X f of X here, then this will correspond to the in X cross R squared line corresponding to f of X. So yes, in this sense, we can also view it as the correspondence with the graph of this, of such a continuous map. But we also have to do this identification here, or not identification, but this translation from RP1 to R squared. Did that answer the question? Okay, glad to hear. All right. So yeah, as I was saying, here we have And this turns out that actually just one more thing before I say why this means that this is the right space. It turns out that actually something more is true, that we don't have just such a correspondence, but turns out we have we have something which I will call tautological line bundle on RP1, which is such a subspace of RP1 cross R squared. And the picture here is that if we take this point, okay, so we saw that RP1 looks like a circle, and every point and to every point there corresponds a line. And then this tautological line bundle is actually the subspace in which over every point we have, how do I draw this? Over every point we have such a corresponding line in the subspace chosen. So I will not try to make this image any more like accurate, because we have such because we have this identification of two opposite endpoints. If you think about it, then this entire subspace is going to look like a Mobius strip, where you start with a line in some orientation, and as you go the whole way around the circle, the line will rotate by 180 degrees, so that the whole thing is so that over every point, every possible orientation of the line appears exactly once. So we have such a tautological line bundle, and then we have that such that every subspace of x times r squared as above comes from what I will call a pullback of this via some function f x to rp1. And what does pullback mean? Well, in a sense, this is just repeating what I have said above. So via continuous. If we have any function like this, then basically we can pick out lines in x times r squared, such that the line over this point is the one corresponding precisely to this image. So we are looking at the line in this bundle over RP1, and we are taking the same line over X, corresponding to what the image of the f of little x was. So just to summarize, this means that this one-to-one correspondence is also not just somehow completely arbitrary, but it itself comes from a certain subspace of RP1 times R squared. And something similar will hold for if we replace RP1 and R squared with R to the n and RP n minus 1. If you know some category theory, then I will also throw in some buzzword that this means that RP1 and the tautological bundle, such a pair, it represents a certain functor. which takes a space X to oh sorry. I guess technically what I have to say is that so this is going to be abstract. It is abstract and this is nonsense, but I want it to be correct. So RP1 represents this functor. X goes to the possible families of lines over X. So here the keyword is represents. There is this notion of a representable functor, and this tautological line bundle is a universal object. Those are two notions which have formal precise sense, which I am not going to completely explain right here. But if you unravel the definitions, then this is basically what I have just said above. Okay, and all those conditions, so these are the conditions that are satisfied, and all of those means that RP1, so all this means that RP1 is what is called a fine moduli space for families or for families of lines in a plane. So not only do points of RP1 classify lines in a space, but also we have it somehow correctly classifies families of those lines. And that's pretty much the end for this extended example. All right. So now that I have explained kind of via this example of fine moduli space, via this example of RP1, what a fine moduli space is, I would like to talk about certain more complicated moduli problem, so classifying some other objects, but in a completely different context. And there I will be even less formal as to why exactly the spaces constructed will be actual moduli spaces. So the examples here, they come from the theory of elliptic curves. In my abstract, I have mentioned that some familiarity with elliptic curves will be useful for this, but it turns out that I actually won't be using anything specifically about elliptic curves. But instead, I will be talking about kind of in more concrete language about lattices in C. We got a question. So I said that RP1 gives us the Mobius strip, and what does RP to the n give us? So I don't think the resulting space kind of this tautological line bundle over RPN, I don't think it has any other as nice description as we have for RP1, because RP to the n itself is kind of more complicated space. So here we are kind of lucky that RP to the 1 actually is just a circle. For general RP to the n, there's just something more complicated. I don't think it has quite such a neat description. So that was a non-answer to the question. Okay, so going back, I don't actually need to know much about elliptic curves. I will be just working with lattices in C, or if you prefer, working with a complex tori. So complex tori, just to briefly mention it, they are just things which are quotients of C by lambda, where lambda is some lattice. But again, I won't be using this. Okay. But now, what is a lattice? So there are many things called lattices in mathematics. So the definition, let me just drop the definition here. So a lattice. So this is a slightly ad hoc definition for my purposes. You can define it more generally. So a lattice in C is a subgroup of C with addition, isomorphic to Z squared, which is not dense. Which is, oh, sorry, no. I don't mean not dense, which is discrete. So that's also an illustration of this. If we consider complex plane like this, then we can just, here we have the origin, we can just pick out some two non-collinear points, not collinear with the origin, and then consider the subgroup they generate. So we are going to have a bunch of points like this, which are going to span a subgroup isomorphic to the squared. And this discreteness conditions. So this is an example of a lattice, an example of non-lattice would be z plus square root of 2 times z. So we are considering things which are of the form integer plus square root of 2 times integer. This will also, since square root of 2 is irrational, this whole guy will also be isomorphic to the squared. But this, the subspace, as a subspace of C, it is not going to be discrete. It is going to be a dense subset of a line. So that's not allowed. I'm only interested in things which are kind of like proper lattices in this sense. And how, in what way I am interested in those? So if I were interested in just lattices as they are, then the classification problem would not be terribly difficult. There would be some things to do, but it wouldn't be all that interesting. But I am interested with them interested in them up to homophety. What does up to homophety mean? It means that up to multiplication by a constant alpha in C star, which means that I identify two lattices as being the same if they differ by scaling up or down or by some rotation. If I have a lattice like that, then if I take some non-zero element or non-zero basis element, so an element of some basis of the space, then I can assume if I'm only interested with them up to isomorphism, then with those lattices up to, sorry, not isomorphism, up to homothety, then I can assume that lambda is equal to z. So I am multiplying by the inverse of this element, so that this whole line goes to is kind of scaled and rotated, so that this guy goes to 1, and we have z here. And then by taking the other generator, is going to be some tau z. So z, and then where tau is not equal, tau is not a real number. Right? And with that in mind, we can again try to see to what sense this tau completely determines. Well, okay, sorry. So tau, if we fix some number tau, which is not real, then this lattice is well defined. And we are going to have those, and it is going to give us all those lattices up to homotopy. But different values of tau are going to give us can give us the same lattice. And here is one simple example of that. So different tau can give homothetic lattices. So the example I'm going to take, the first lattice is going to be pretty much the simplest one you can think of. So I am going to take the integers here, and I'm going to take tau to be equal to I, just the imaginary unit. So the lattice we get is just the rectangular or even square lattice in the plane. The second lattice I am going to take is going to, it is still going to contain the integers, but instead I am going to take tau to be equal to 1/2 plus 1/2 I. So what I am going to get is pretty much the same lattice as above, but we are also going to throw in centers of every square in this lattice. So it may look like a different lattice from this one, but up to homotopy, they are exactly the same, because we can, if we rotate this lattice by 45 degrees and scale by a factor of √2, then we are going to get the same lattice. Yeah, so we have a question. Okay, there's a never mind. So I am going to ignore it because I think there's some confusion. Okay, so we see here that those two values of tau are going to give us different but homothetic lattices. And if this is the case, then the question remains of which when are two different values of tau are going to give us a homothetic lattice. Or I'm going to answer this question slightly differently. If I am given some value of tau, for example, tau equal to I, then what other values can I take for tau to give us a homothetic lattice? And okay, and how is that going to work? Well, to get a homothetic lattice, which is also of this form, I have to pick out two basis vectors. So for example, let me pick out, say, this vector here and this vector here. So this is going to be a plus b tau for some a and b integers, and there's going to be b plus d tau. And I want them to be a basis vector. It turns out that they are a basis vector if and only if, sorry, not that they are basis vector, that those two vectors form a basis, if so, basis if and only if AD minus BC is equal to plus or minus 1. If this reminds you of the determinant, then there's a very good reason for that, but I'm not going to get into details of that. And now if we have those two vectors like that, then I can rescale this lattice so that this vector here goes to 1. And then this other value, after dividing by this value, is going to give us a new value of tau, which is going to give us a homothetic lattice. And it turns out that all the possible values of tau that we can achieve this way come from such a quadruple ABCD. So what this means is that given some tau, other values which give homothetic lattice, excuse me, are A plus, actually I'm going to slightly change my notation because tau plus B, C, tau plus D. It doesn't make much of a difference, but it is a bit of a technical convenience. If we write it as A tau plus B over C tau plus D, where AD minus BC is equal to plus or minus 1. If we were to restrict, because we can also clearly replace tau by minus tau, so that we can just flip the vector around the origin, we can always assume that we are taking some taus from the upper half plane, so they have positive imaginary part. If we were to do that, then we could restrict ourselves to matrices, to ABCD, which satisfies this with plus 1. So you often see in literature that they are just taking the positive values, but it doesn't make much of a difference. Okay. So now that we have identified all of those possible guys, then it is possible to do something similar to what we did at the beginning with, in the case of the projective line. So what I did at the beginning is, so let me quickly scroll up to the very beginning. When I was trying to form those spaces classifying lines in a plane or the 3D space, then what I did, I took some subspace which almost contains all of the, which almost contains one unique representative from each of those classes, except there were some issues at the boundary, which we had to fix. Using this description of values of tau, something similar is possible here. I will not explain exactly how this is done, but what we get is, so from this, we can construct what is called a fundamental domain. And in this case, And it is going to be a subset of the set of possible values of tau. So remember, tau was arbitrary non-real number, non-real complex numbers, of course. And I can choose the subspace such that, except for some issues at the boundary, every kind of orbit under replacing tau with such a fraction is going to have exactly one element. And there are many possible choices for such a domain, but there is one kind of canonical or standard choice. Okay, it's not exactly canonical, but it's a pretty standard choice in the literature. And it looks like the following. We are taking, so this is the real line. Here it is going to be the imaginary line, IR. Here I am taking 1, and I am drawing, here's -1. I am drawing a circle, the unit half circle, and then I am considering 2 other vertical lines, which are over values of 1/2 and -1/2. Okay, this one turned out a little weird. And then this region here, between those 2 lines and above this unit circle, this is going to be the fundamental domain. And the way you have to identify the edges is basically you have to fold this whole thing in half. So first you have to identify this edge with this edge, and then you have to also identify this arc with this arc, or going this way, like this. So this point here is fixed, and then we identify what's on the 2 sides of it. Okay. And now if you think about what it looks like after gluing all those things, it is going to look like a cylinder which is kind of capped from one end. And it is going to like extend infinitely like this. It's going to extend infinitely above. How do I identify the arcs? Okay, so let me just write it down. So we identify, so on the boundary, identify x plus iy with minus x plus iy. So on this boundary, where we identify each point with its mirror image. And that's the only identification we made. We make the interior here is left intact. Okay, so as I was saying, this glued space is going to look like a cylinder, but we can also think about kind of unfolding this cylinder. So I am going to say that this glued space is homeomorphic to a plane. Would it look more like a cone? Well, you could argue that it looks more like a cone, but they are homeomorphic, so it doesn't really matter. It is a cylinder which is kind of capped on one side, so I suppose maybe cone is more apt. Okay. I have about 10 minutes left, so let me slowly start to wrap things up. Okay, so we have formed this space, but then we can ask the question, just like above, just like we had at the beginning, is this the right space? So of course it is going to, the points of the space are going to identify, are going to classify all of those lattices up to homotety by the arguments I have explained before. But again, there are many other natural choices, and we are asking whether this is the correct one in a some whatever sense. And the answer is no, but yes. So the answer is no, in the sense that this is not this is not a fine moduli space. Moduli space. And the reason for that essentially comes from the fact that there the lattices have automorphism in some sense. So you can take, for example, if we consider multiplication by -1, then every lattice is going to be mapped to itself. And it turns out that for the purposes of the moduli spaces, such automorphisms are going to be an issue. And whenever they are, you have non-trivial automorphisms, then the fine moduli space is very likely to not exist. However, it turns out that it is, yeah, so this is not a fine moduli space, and there isn't a fine moduli space. But it is the best we can get. And this is going to turn out to be something called, yeah, so I don't really have much time to properly explain the automorphism argument. I can explain it at some other time after the seminar, but sadly I don't have time to present it now. The question, basically the claim I am making is that automorphisms are bad for fine moduli spaces. I'm not explaining why. I can explain it some other time. So there is not a fine moduli space, but it is something that is called a coarse moduli space. Which very briefly, okay, I'm not going to say what it exactly means. It can be stated in terms of in categorical terms, that this is somehow some initial objects out of the ones trying to represent this a functor in some sense. So in that sense, and this also guarantees that this space is a unique one with this property. So in this sense, it is kind of the right space for a slightly different reason, but it is also a right space. All right. And in the last, hopefully, just 5 minutes, I would like to say one way to fix this issue and actually get something that is a fine moduli space. So here is a fix to the problem. And it's something called the level structure. And it basically means that we are restricting the number of automorphisms that we are allowing. And the way it works is that when we consider our lattice in the space, then we consider not only just the points of the space, but we also distinguish some point in the space. So we are considering per lambda, but we are also considering something of the form z plus lambda. So this is going to be a coset of the subspace such that n z belongs to lambda, where n is a fixed number. So we are considering, if we think about the quotient space C over lambda, then we are picking some n torsion point. But precisely we want it to be a point of order exactly n, but yeah, let me not get into those details right now. And now when we are considering kind of some homotheties between different lattices, then we are distinguishing lattices if this torsion point is chosen somewhere differently. So because this is modulo lambda, then this point kind of repeats itself, but there are multiple choices for it. For example, we could also pick some torsion point here, which would be different. So we, even though they are the same lattice, we consider them distinct because we chose different torsion points. And then one can show by an argument similar to the one above that so by scaling may assume z is equal to 1 over n, and then given some tau, other tau which work for it are, so which give like an isomorphic lattice, but also looking at this point, at a certain point, they are going to be a tau plus b, c tau plus d, where ad minus bc is again plus or minus 1. But we also require that kind of this matrix, let me write it briefly, is congruent to 1, 0, 1, and something here. So A and D are congruent to 1, C is congruent to 0, and B is whatever modulo n. And then we can similarly congruent entry-wise. And with that, we can consider fundamental domains. They are not going to be quite as neat as they were for n equal to 1. So without the torsion point, basically, but you can still consider them. And resulting quotients, which are in the theory denoted by y1 n. Due to lack of time, I won't explain exactly where this 1 comes from. But it turns out that they are fine moduli spaces for n greater or equal to 3. So as soon as n is greater or equal to 3, you get rid of all the automorphisms, and the resulting space does turn out to be a fine moduli space. However, the argument that it is quite a non-trivial one. But yeah, those spaces, those fine moduli spaces, are of a lot of importance in number theory. And they have a lot to do with many other topics in like in number theory, like modular forms, or like many other topics in elliptic curves, which are like that. Yes, so basically, yeah, as you say, as the comment says, we basically look at a finer family of lattices to get a better moduli space. With more information, we kind of have a better control of what the automorphisms are and whatnot, and that gives us more understanding of what the modular space looks like. But yeah, this is it for my talk, and yeah, thank you everyone for attending.